So there's one thing that I missed pointing out for batch normalization. You see, when we are calculating loss for dev set or when we do it for test set, so what we did is we are calculating mean and standard deviation over this entire dev set, which ideally is not correct because we should take the mean and standard deviation that was calculated from the training set and then use that mean and standard deviation to standardize or normalize uh, the H-React here. Therefore, what we'll have to do is there could be two ways of doing it. Once the training is completed, we can separately run a few commands to calculate the mean and gradient, mean and standard deviation for the whole training set. Or while the training runs, we can keep doing calculating the running mean or running um, standard deviation. So let's do it separately. So this would be with torch.noGrad. Let's copy the commands from here. You need to calculate the H-React for the entire training data. We don't need these. Instead, we can say that bn gain or sorry, bn mean is this part and bnstd is this part. And once we have done this, we have our bn mean and bn standard deviation for the entire training data, and then we can let's calculate this, and here we can instead use bn mean and bnstd. So this would be now correct way to do it. We are not calculating the batch normalization mean and standard deviation for the dev set, but we are calibrating it from training set and then using it in the dev set or test set. Now let's also quickly work on making a code look more like a PyTorch code and layers or networks, because right now it's very much all broken up and manually written. So let's modularize it and we can, I'm sorry, let me just, okay. So this part of the network, things happening here, we can modularize these with PyTorch-like syntaxes and objects. So basically what will happen is, um, what happens here is matrix multiplication, this becomes a linear layer. This all the batch normalization related operations, this becomes a batch norm layer. This becomes a 10H layer. Like we are using dodge.10H, we can also write a custom 10H. Then this again becomes a linear layer. Then this would be same because we are already using PyTorch function now. So let's construct three different classes. class linear. We need self.weight and self.bias for this, depending upon fan in. So fan in and fan out is terminology of the uh, PyTorch. Basically, this is the fan in is input number of features that are coming in, and fan out is the number of neurons or output, how many neurons output will be given. So this would be, we can initialize this as torch as rand in, fan in by fan out, and we can also do scaling as per our timing method, or our methods that we followed, that we went through while doing the uh, this scaling here. So in linear scaling would be done always that divide by, it will get divided by fan in, square root of fan in. There would be some gain, but that depends on if there's a activation layer non-linearity after the linear this combination or not. So we can handle it later. Equals to, and if bias else. Next function we would have is call method. So we'll pass x to it, and we'll calculate the output. Output is x at the rate self dot weight if bias out plus equals to bias else. Else will return the output of this, or rather let's say self dot out. We can make one more method in this, which is to calculate the parameters. Self dot weight plus this, if self dot bias is none, else self dot bias. So we'll return parameters will be self dot weight plus self dot bias if bias exists, otherwise just the weights. Okay, so this we have defined our linear function. Now let's define our tanh. So for tanh, there won't be any need for initializing it because we can directly call the call method. So we'll equals to dot tanh x out. And we can also define a parameters method to take self, and it will return empty because there won't be any trainable parameters in damage. Now let's go back to batch norm class. So here let's initialize. So we'll need dimensionality as a parameter. Self dot epsilon. So let me bring in the paper, the algorithm that was mentioned in the paper here. Or maybe we can go through the PyTorch patch normalization. Okay, so in PyTorch, this kind of batch normalization is named as batch norm 1D. Uh, Maybe we'll also use the same naming convention. Okay, so if you see here, this is named as batch norm 1D. Maybe let's also do 1D. So what it does is it takes input as number of features, which is dimensionality we took in as. Epsilon is a factor added in the denominator while in standardizing the entire layer. Momentum is basically a parameter used to run the uh, it's kind of a bn gain and bn bias kind of parameter that is used to calculate this with this momentum. So what we'll do is for now let's just keep self.dim and self.epsilon. And one thing is because the batch norm 1D has different behaviors while training and while not training or inference. So we'll take a flag which will say true and epsilon dim. So once we have our we'll also need to declare or initialize self dot bn gain, self dot bn bias. These would be nothing but torch dot ones, self dot dim, torch dot zeros, self dot dimensionality. Now let's define call method. If you pass on x, what happens is so behavior if behaviors are different, we'll call self dot if self dot training. Then we will calculate self dot mean equals to, or rather say x mean is equal to dot mean 0, keep them equals to true, x variance std variance equals to x dot var 0, keep them true. We have calculated these two. If this is not the case, then x mean is so. You see how we in our previous explanation how we separately ran a cell to evaluate the to calculate the BN mean and BN standard deviation and make them fix for the entire training set. There's another way which we can do here is while training with each iteration we can calculate the running mean and running variance. So to do that, what we can do is we'll basically let's define them as self dot running mean dot running variance. Okay, so self dot running mean we can initialize as torch dot zeros because we want things to be unit Gaussian, therefore it should be close to zero of dimensionality. This has torch dot ones of the same dimensionality. Now when the we are in the training mode, we can also update it running mean and self dot running variance as. So there's another parameter in the in this sorry in this definition here you see momentum. So this momentum has to be used uh, while calculating the running mean and running variance. So that would be something like 1 minus F dot momentum. We'll have to initialize momentum here. So self dot momentum into self dot running mean plus self dot momentum. Okay, so while training, we'll keep calculating our running means with the proportion, majority portion coming from, let's say we start, because in PyTorch modules, we see that it is initialized to 0.1, right? And epsilon is 1e minus 5. So just say that we do the same here. Momentum is 0.1, epsilon is 1e minus 5. So then majority portion, 1 minus self dot momentum is basically zero point 0.9 times of running mean and zero point 0.1 times of x mean. So we'll keep on adding x dot x mean here. So yeah, we have calculated a running mean and variance. We'll keep on updating this with a small proportion coming from the current batch's mean or variance. Then when when we are not training, x mean will be self dot running mean and x variance will be dot running variance. Um, so now we can again say if self dot training Now to do this, we don't have to do self-dot training. In any case, we have to do it. We'll say h preact is x minus x mean divided by, so if you look at the formula here, it is x minus mean divided by the square root of variance plus epsilon. So we'll also do the same. Torch dot sqr square root of x bar plus self dot epsilon, and this would also multiply with the gain and offset with the bias. So here, because it's mentioned it's gamma and beta, we can change the nomenclature. Instead of B and gain, we can say gamma and beta. So then self dot out is self dot gamma times h preact plus self dot beta, and we'll return somewhere self dot out. But before that, one more thing what we should do is, while we were calculating these, updating these running mean and running variance, we should say with torch dot no grad, because these are not the trainable parameters, and we can not we can ignore it from storing the gradients for. Uh, so yeah, this will be done. Then we'll define parameters. So here the trainable parameters are gamma and beta. These two are not trainable parameters, and these are all hyperparameters. So we'll say self dot gamma plus self dot beta. Alright, so we have all our modules defined: linear, tanh, and Vaishnav only. Now we can build a network again. So we'll have to input to this would be vocab size, and output will be embedding dimensions. Then we can build layers. We'll make a linear layer with fan in as input to this would be um, embedding dimensions multiplied by the block size, right? Yeah, so block size multiplied by embedding dimensions, and output would be dotted line. We'll take in tan h here, tan h coming up here. Next would be hidden dimension would be the input. Output would be vocab size, and then we might not need to do tan h, or if let's say we are going to increase our number of layers, we can still do it. Vocab size and here we might not need the 10 inch. So this is our layer, first layer, second hidden layer, and then the output layer on which we'll get the logits. So this would initialize all of the layers for us. Then one thing we have to remember is while initializing the linear layer, we scaled it with square root of n, but we did not apply the gain. So for these two layers where we are applying nonlinearity, we might have to apply the gain. So to do that, for Ln layers, mm, for Ln layers -1, that gives us these two layers. We'll say self dot weight multiplied by 5/3, because for 10 is the gain is L dot weight we multiplied with 5/3 as the gain. Then if the layer is okay, so also if you remember in the last layer, because we were getting logits that were very large and thereby our soft maxes were not performing well. So So what I mean by that is when we are looking initially, our initial loss, first iteration loss was coming to be a large number like 20, 30, 40. But that was happening because of logits numbers going in large. So that to do that, to control that, we scaled our last layer with 0.1 multiplier for weights. So here also we can just say that layers -1. How do we define it? Dot weight. We multiply it with 0.1, and we can also say layers -1 dot bias equals to 0. Yeah, so this is all our initialization done, all the scaling and gains for the layers, linear layers applied. Now we can just say parameters equals to, for p in parameters, mm, or no, that's the last way. For L in layers, for p in L dot parameters, we have to just say p dot numer, and we need to sum all of this. Okay, so that we'll do later. This plus C. These are the parameters to be learned. And also one more thing for in parameters, we need to turn on the requires grad for true everyone. Um, e dot requires grad equals to true. So yeah, this is the initialization done. Linear object is not iterable. What does that mean? Mm, Okay, so there was a mistake uh, that was made. If we run this, there would be error that linear object is not iterable. So basically, when we are iterating through all the layers, because 10H layers don't have the weight parameters, therefore I'll have to say that here, if there is an instance of L is linear, only then let's do this. So this should um, okay. All right, so we have now 58,000 parameters, and all our parameters are scaled, gain applied. Then we have a parameters variable defined. We have all requires grad equals to true. So now we can start our training part. Let's copy this from here directly. And also the hyperparameters. Where did it go? Okay, I think I should put them here. 10 by 100 by 64. So the number of parameters is C to C. Oh, sorry, 100 here. So we have 16,000 parameters. Now what we need to do here is we make a batch of data. Embedding equals to C index with XJ, XP. And then from here on, for layer and layers, X equals to we also need to m concatenated is m dot view minus 1 samples would be as is. This would be block size times embedding dimensions, right? Yeah, or it could be the other way around, but it's okay. We can say m dot fill dot shape 0. This should also be okay. Let's see this x equals to cos x squared. Keep on updating this. So at the end of all of this, we would have uh, this coming out. The x would have the logits. Therefore, we give pass an x here, and the remaining things should be the same. All right, let's try to run this. This equals to so I think uh, you have to say here is not none. Cannot access the way out where it is not related with the value. Let's just say, oh, okay, all right. Then no mistake. Self dot out. Cool. So we are training the network now. Okay, I think we made one mistake, one more mistake. We have to add batch norm here. Mm, After each of these layers, instead dimension would be unhidden. So in both these layers, we would have batch norm, not in the last layer because we are not doing any activations there. All right, I'll just let it run for a few minutes. One last piece now. Let's also try to calculate the loss for our entire dev data. So what happens here is cool. So we are still reaching at the same loss that we were 2.0975. So even with introduction of with all the PyTorch-ifying, we were able to achieve a previous result, kind of. So it's not a nothing wrong is going on. At least everything is functioning normally as it should. So yeah, this is what I wanted to achieve with this video. Basically by toxifying each of the layers and the training and inference, etc., understanding how batch norm works, and so on. So yeah, thank you for sticking with me. I'll be wrapping up now.